Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
As you depart from the natural genetic code, it's harder for viruses to infect you because viruses require your cells to recapitulate and produce their proteins for them. And so these new organisms being resistant to viruses is unlikely to pose a major threat, but it was a real question, right? What would happen if one of these organisms escaped into the wild? So the project I did with George was actually around biocontainment. We asked, could we take these new building blocks and create enzymes that are essential for life within this organism that require these new amino acids? So that if you took away that amino acid, these essential enzymes can't function and the organism can't survive. And so it took quite a bit of work, the design side and on the strain engineering side. But in the end, we created organisms, multiple enzymes that were essential for life and composed of these new building blocks. So if these organisms escaped from the lab, they couldn't survive.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Daniel J. Mandell, Ph.D., Chief Executive Officer, Co-founder, and Director of GRO Bio. So we're going to talk about his work there. So Dr. Mandell, thank you for coming.
Thanks, Richard. It's great to be here with you.
Yeah, tell me a bit about, first, if you would, your background and how you came to GRO Bio and to start it, and then I want to ask you about GRO Bio itself.
Yeah, absolutely. So I was originally trained in AI and machine learning out at Stanford and got very excited about how these tools could be applied to modeling biology. I was actually, at least in my mind, pretty subpar biologist when I was back in high school. And I kind of saw computation as a way to start asking some of the questions that I felt I couldn't really address in the lab back in the earlier part of my studies. And from Stanford, I went on to do a master's degree in AI and bioinformatics at Edinburgh in Scotland, and started using machine learning tools to try to predict protein interactions really before that was a feasible question to ask. And so while I think the project was perhaps a bit misguided at the time, it got me really excited about understanding the systems I was working in. What are proteins? What actually is an amino acid? And what drives their functions? So I went on to do a Ph.D. at UCSF in a field that we call computational protein design. And here I was actually really able to bring in these techniques from not only machine learning, but also robotics to model how proteins can move, what we call their conformational dynamics, and how those properties are affected by changing the protein sequence. And so one of the things that really struck me about proteins is that they're all built from these same 20 amino acid building blocks. And as we're modeling them and trying to design new functions, you can almost feel restricted in a lot of ways by having only these 20 building blocks to work with. And you might actually have a very clear picture, a different chemistry or a different shape that you want to build into a particular protein, and you just don't have access to it. And so I really fell in love with the field, and I had this fantastic PI, Tanya Krotemi, who spent countless hours with me staring at design protein structures, really imbuing in me how proteins fold and how they function. And so when I went off to do my postdoc, I ended up working with George Church at Harvard Medical School. And when I got there, they were just finishing these new organisms that really for the first time can take us beyond those 20 standard amino acid building blocks. And so as a protein designer, this was really epiphany for me. For the first time, I could start to think about bringing an unlimited set of shapes and chemistries and functions into the protein universe. So I spent about 6 years with George as a postdoc, combining these two worlds, this one world of designing proteins with new amino acids, but now within this organism that can actually, for the first time, put these new amino acids into these proteins. So combining the designs and an actual organism.
So you made new amino acids that haven't existed until now, but they have the characteristics whereby they could assemble and form proteins?
That's right. So these amino acids, we call them non-standard amino acids, or NSAAs for short. And you can think of them as, new colors in the palette or new letters in the alphabet. At the end of the day, they're like new Lego pieces that we can build with. And each one has a special property that can potentially be useful. So with George, the first question we asked is, can we actually rationally design proteins using these new building blocks? And if we could, what would be the point? What would actually be useful about this? And so at the time, as we were creating these new organisms, there were some questions around the safety of these organisms. For example, the way that you modify the genetic code of these organisms to allow them to use this expanded amino acid alphabet confers them with certain advantages. For example, as you depart from the natural genetic code, it's harder for viruses to infect you because viruses require your cells to recapitulate and produce their proteins for them. And so these new organisms being resistant to viruses, is unlikely to pose a major threat, but it was a real question, right? What would happen if one of these organisms escaped into the wild? So the project I did with George was actually around biocontainment. We asked, could we take these new building blocks and create enzymes that are essential for life within this organism that require these new amino acids? So that if you took away that amino acid, these essential enzymes can't function and the organism can't survive. And so it took quite a bit of work, the design side and on the strain engineering side. But in the end, we created organisms with multiple enzymes that were essential for life and were composed of these new building blocks. So if these organisms escaped from the lab, they couldn't survive. And this was really the first time. So this was really the first time that I think we felt confident that we could rationally engineer proteins using these new building blocks. And it was around that time that we turned to the question of, hey, this is a very potential powerful technology. What are some of the unmet challenges in the clinic in medicine that we could potentially solve with this expanded amino acid alphabet? And that was really the genesis of GRO Bio.
So when you say organisms, what do you mean? You've created what? Bacteria, or what kind of organism did you use as the chassis, and how is it modified?
Yeah, exactly. These are bacteria. They're a derivative of a strain of bacteria called K12 E. coli. This is E. coli kind of has a bad name because of its role in food sickness, but there are many different strains of E. coli. This happens to be one that is generally regarded as safe. And it's in fact utilized in industry already to produce a variety of products. What we did was reprogram its genetic code to now allow the expansion of the amino acid alphabet. So it's really sort of a new organism that derives from a very well-studied organism that's used both in the laboratory and in industry.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
So was there a need for this? I mean, how many proteins could be made from the basic 20 amino acids? I would think a whole bunch. Or is this more of a, let's see if we can do this type project?
That's a great question, and it's a great question because if you look at the diversity of life, life has been able to build everything we see around us with these 20 amino acid building blocks, right? So why do we need more than 20? Well, the answer is, life has had 3.5 billion years to build all of this, and life's goal is to survive and to replicate itself. We as human beings have somewhat more precise goals. If you have a disease that results from a faulty gene or a faulty protein, we don't have 3.5 billion years to wait for a solution. We need to engineer a solution. And engineering is made more powerful, right, when we have more tools at our disposal. So by way of example, one of the key new properties that GRO Bio is building into proteins are amino acids that have sugar molecules on them that can dictate how the immune system responds to that protein. And with those sugar molecules, these are called glycans, we can turn the immune response on or off. And so we're using these to try to reverse autoimmune disease and also to make therapeutics that don't raise an immune response like many current therapies do. And so that isn't possible using the standard 20 amino acid alphabet.
Yeah, quick question here though. What would you, if all this was approved, what would it look like? You would inject amino acids into someone, or you'd build proteins and you would inject that into them, or would you attempt to get them to make the proteins themselves by, altering their cellular function? Like, how do you think this would work?
Yeah, great question. So at present, all of our therapeutics are proteins. And the way, for example, this would apply to autoimmune disease would be recognizing first that when you have an autoimmune disease, your body has decided that some protein or cell within it is foreign and therefore mounts an immune response to it, right? So for example, in type 1 diabetes, oftentimes your body decides that proinsulin is foreign and mounts an immune response to proinsulin that ultimately results in the death of insulin producing cells. And many autoimmune diseases are sufficiently characterized that we know what that protein is that you're responding to. That's called an antigen. Or in the case of an autoimmune disease, it's called an autoantigen. So when we know what the autoantigen is, we actually have an opportunity to re-educate the immune system to understand, hey, this is a self-protein. This is a protein we shouldn't be reacting to, right? So the way we do that with this technology is to take that exact same autoantigen and express it in our bacteria, our GRO platform. But now we can decorate it with these special glycosylated NSAAs, these non-standard amino acids. And as I mentioned before, these special sugar molecules are the signature by which your body distinguishes self from non-self. So we take that protein bearing these NSAAs and just administer that to the patient. And in so doing, you then can re-educate the immune system to recognize that protein as a self-protein, because now it has this tolerizing signal on its surface. And you can develop actually a memory of that via T cells. There are specialized T cells called T regulatory cells, whose job is to recognize your own proteins and turn down the response to them. And what we're doing through this process is by administering this autoantigen bearing these tolerizing glycans, we're ultimately creating a population of these T regulatory cells that will then turn down the immune response to that antigen. Those T regulatory cells actually go off and downregulate or cause energy in those overactive T cells and ultimately repress the production of antibodies against that antigen.
All right, so you're conditioning the person first to accept it, and then what? Once they accept these without a significant immune response?
So for autoimmune disease, that's really the end game. Once you have a population of T regulatory cells that can turn off the response to that protein, the balance shifts in your favor. And the intention then is that those T regulatory cells do the work from that point out. They will, if they encounter T cells that are responsive to that antigen in your body, they will actually cause energy or deactivate those T cells.
Oh, I misunderstood. So with these extra sugar molecules attached to the protein, the immune response is dampened. So it's still the original. Is it still the original protein? It just has extra sugar molecule on it, or is it now identifying something new? Like, how does it know that even though this thing is new in the body, and it develops an understanding of it where it won't attack it, that it still would not attack the old? Because they do have different. I guess they're different structurally and functionally, but not enough that that the old version gets rejected now or attacked?
Yeah, that's exactly right. So what we're administering is the exact same protein sequence as the sequence they're reacting to, but it has this tolerization signature on it now, these glycans. And the way that the tolerization becomes persistent is by the induction of those T regulatory cells. So there's basically an immune cascade that gets kicked off by introducing that glycosylated version of the antigen. And the end result of that pathway is to create these cells that didn't exist before, these antigen-specific T regulatory cells. And they're really the soldiers, if you will, that go off and do the work. They say, okay, I'm responsive to this antigen, but I'm a tolerizing T cell. And when they encounter the T cells that are reacting to the antigen in a stimulatory way, they turn them off. So those T cells, those T regulatory cells have a long lifetime. So they can actually persist and basically maintain a memory of the antigen as being a self-protein. So it's always this dance between the tolerizing T cells and the stimulatory T cells that are reacting to your copy of the antigen. But what we've done is shifted that equilibrium towards the regulatory side to turn down the immune response. And it may actually be necessary over time to get an occasional booster of that glycosylated antigen to keep sort of reminding the body, hey, this is a self-protein. The mechanism by which that happens is to create, more of those T regulatory cells. But at the end of the day, it's just a protein that sends a signal that says, the sequence you've been reacting to is actually a self sequence. And the mechanism by which that's memorized is via the creation of those T regulatory cells.
Yeah, I was going to ask you, so there'd be a couple of administrations of this, and then maybe once a year, let's say, there would be an update booster on it. And it would keep the person from having significant autoimmune response to a certain condition. Is that
exactly,
right?
Exactly right. And I think what you're noting there that's so important is that you're turning down the immune response only to that one protein. So right now, if you have an autoimmune disease, for most autoimmune diseases, you have to be given a broadly immunosuppressive therapy. You turn down the immune system overall. And you do that because for some autoimmune diseases, it makes the patient so sick it's worth the sacrifice of turning their entire immune system down. But that's awful for most people in terms of side effects. It makes you very susceptible to infection. And you see this with COVID, right? People talking about being immunocompromised. Many of them are immunocompromised because they're taking drugs that turn down their immune system for one reason or another. It also potentially leaves you vulnerable to cancer. One of the ways that your body fights off cancer is through the immune system. It recognizes that a cell has gone haywire and it kills it. If you turn down your immune system, your risk of developing cancer goes up. So, we really want to move away from these broad immunosuppressive therapies and towards these therapies that are what we call antigen specific. We want to turn down the response or tolerize, as it were, the patient just to that one protein that they're reacting to.
What about the opposite effect? To do maybe a slow pseudo-vaccination type effort that would be the opposite of giving tolerance, the taking it away, or sensitizing the system very specifically.
Absolutely. Yeah. So everything I've talked about today is using this technology for tolerization. But as you put it, you could just as well use it for sensitization or stimulation, right? As a highly specific vaccine towards something. And you could imagine using that technology to stimulate someone towards an infective agent, just like you would another vaccine today, or even towards a cancer cell, right? You could generate a very specific response to a particular cell marker that's overexpressed on cancer cells. That's an approach that is currently underway through a variety of different technologies, and it's definitely on our radar. The reason why we started with tolerization is that in a way it's actually harder. There are a lot of ways to activate the immune system, but it's actually much harder to create a very specific tolerizing response. And part of the reason is that it hasn't been possible until now to create these proteins where you can precisely define that glycan composition on the surface. We think this is really a differentiating approach because we have a production system that lets us do this. And, this is coming back to your initial question, why is this important? To our knowledge, there isn't another expression system out there that can make precisely glycosylated proteins. And that's just one example of something you can do with standard amino acids that we think is unique to our platform.
Well, what do you think would be some of the off-target effects that you'd have to control?
Yeah, it's a great question. We hope that this is extraordinarily specific. All we're doing is putting the one protein in. And outside of that, there's no mechanistic reason to believe anything would happen with other proteins in the body. Now, of course, you don't know till you get there, right? Every therapy has to be run through both preclinical and clinical studies. What if there was some other protein that was highly homologous to yours, that had a very high sequence identity, and you end up tolerizing something you don't want to, right? These are all things that are very difficult to predict. You can certainly do analyses ahead of time to minimize the risk. But like every therapeutic, you have to kind of run it through its paces. I think what we're doing here is really trying to stack the deck in the patient's favor and make it as unlikely as possible that there are side effects because of the exquisite nature of the immune system. When we give that glycosylated antigen, the body's immune system, as you probably know, is very finely tuned to specific sequences. And while it can and does make mistakes, this does give us our best chance to create a tolerizing effect that is specific only to that protein. And in fact, another advantage that I might mention is that because you're giving the whole antigen in a tolerogenic context, you're also tolerizing the patient to the entire protein. A lot of times in an autoimmune disease, the body starts by reacting to just a piece of that protein. But what happens is, as inflammation kicks in, the immune response spreads to other parts of that protein. That's a phenomenon called epitope spreading. And so, our hope is that we can actually tolerize the patient to all the different parts of that protein, because that's what we're giving them, right? The tolerogenic version of the whole protein. And thereby not only, head off this particular antigen epitope at the pass, but all the other epitopes on that protein. So, yeah, go ahead.
Quick question. How does this look for autoimmune type problems versus exogenous? I have a peanut allergy, I eat some peanuts, I get a horrible reaction type situation. Would it work for both, or are you just focused on autoimmune, or what would be different about the two?
Yes, in principle, it works for both. So in all cases, we need to know what the antigen is and have some kind of understanding its mechanism. So for example, there are autoimmune diseases that would be challenging for this approach right now, because as scientists and biologists and life scientists, we haven't yet figured out what all antigens are that cause the disease. For example, lupus is a case where the autoantigens are not very well characterized. Rheumatoid arthritis is very complex. Even in multiple sclerosis, it's difficult to know exactly what it is that causes someone to progress from relapsing remitting MS to primary and progressive MS. And so we at our company and other companies that work on antigen-specific tolerization are starting with diseases where we know what the antigen is. The mechanism that we're using, though, can absolutely be applied to exogenous proteins, right? And so things like allergens are definitely on the table, provided you know what the epitopes are, what the antigens are. And in fact, there's another whole set of applications that we're pursuing precisely for exogenous proteins. One of the challenges of giving somebody any protein therapeutic is they're typically engineered or sourced from another organism, which means your body hasn't seen them before, and you mount an immune response. And that immune response often comes in the form of neutralizing antibodies. We call these anti-drug antibodies. So if you have a faulty enzyme in your body, and the best way to treat you is to just produce that enzyme and then give it to you, if that enzyme has any deviation from your natural sequence, you'll oftentimes develop an anti-drug antibody response, and it becomes ineffective over time. So we have another program underway where we've taken an enzyme, which is an excellent therapy for a known metabolic disorder. And again, we create this tolerizing version of it. Exact same process, express it in our platform, decorate it with these tolerizing glycans, and administer that to the patient. Now, whatever sequence we've chosen, it doesn't matter if their body has seen it before or not, because it's bearing that tolerizing signature. It has those glycans on it that all the human proteins have. And so they recognize that as being a self-protein. What that means now is you can keep giving the patient this life-saving therapy without it becoming less efficacious over time, because now you prevent the formation of those neutralizing antibodies.
No, you have a good background. I was thinking, because of your protein folding knowledge. There's people that have conditions where proteins will misfold like Ehlers-Danlos or hypermobility tissue disorder, where, it appears that they have a misfolding of collagen. So I wonder how this could work, maybe to fix that.
Yeah, any case where the misfolded protein is resulting in deficiency of that protein is a potential candidate for a protein replacement therapy. And anytime when you have to give somebody a protein replacement therapy, you have to worry about antibodies to the replacement therapy. And so this would be a candidate for any of those diseases. A third area that we're now pushing into that we're very excited about is for gene therapy. And while we're not a gene therapy company in the traditional sense, we do want to help gene therapy companies create gene therapies that are not immunogenic. So, for example, you might be familiar with adeno-associated virus, or AAV, which is the most commonly used viral vector to deliver gene therapies right now. And we have created some life-saving therapies using this vector. But there are two really important problems. One is that as soon as a patient sees that virus, while it's effective the first time, now they develop a memory of it. It's like they've been inoculated, right? And the next time you try to administer that therapy, it oftentimes doesn't work. And again, it's because of those neutralizing antibodies that get generated. The second problem is that depending on which virus you use, 30 to 70% of humans have already encountered that virus just going about their daily lives. And so they already have a neutralizing antibody titer in their body. If that's the case, they cannot be reimbursed by insurance for these therapies. And that means that therapy is basically out of their reach. These are $1, $2, $3 million drugs. So if you can't be reimbursed for it, you can't get treated. And these are desperate patients in many cases. So those are two really big problems that really both come from the same source, the presence of these neutralizing antibodies. So just like we can do for autoimmune or for enzyme replacement, what if we could administer these viral capsid proteins to the patient, bearing these tolerizing glycans to educate the immune system to them, thereby, eliminating or preventing the formation of those neutralizing antibodies. So this is a new direction that we're really excited about that we're now just getting into. But it's the same process and really the same mechanism. Take those capsid proteins in our strain of bacteria, decorate them with these tolerizing glycans as, these are glycosylated amino acids, and then administer that to the patient. We're not going to be making the capsid probably that delivers the therapy, right? This is almost like a pre-education of the immune system before you deliver the therapy. But it's the same process, right? Let's get rid of those antibodies and let's keep these patients responsive to the treatment.
I was just thinking, it's funny, you don't really do it, but you could tell people you make protein shakes with different characteristics.
Yeah. We should think about that for marketing and trademark purposes. Absolutely.
No kidding. Another question. So I would think this would have applications in aging. I'm not sure if this is right, but as people age, do they experience misfolding and problems producing certain proteins, again, in the right shape or the right abundance? Maybe this could help with certain aspects of aging.
Yeah, I mean, it's certainly possible. And if you look at, aging in many respects is considered to be, in large part a disease of inflammation. They're highly correlated. Could you use some targeted tolerization approaches to prevent certain kinds of inflammation? Is possibly on the table. And then the second thing I would say is that many of the approaches that the field is pursuing to address aging involve delivery of the modifying reagent through a viral vector. And so again, you may need to tolerize patients to these vectors in order to explore some of the approaches that are being used for aging. A lot of this work is being carried out, in animals right now. Some companies are looking at quote unquote anti-aging for dogs. And what this really means is prolongating health span, right? They want to more healthy years. And so there are certain known, cardiac markers, for example, that they're looking to modify. And those can be administered again through these viral vectors. So again, tolerizing the recipient, whether it's a dog or a human, to these vectors allows for the possibility of redosing, which may be necessary, right, over time. Very likely will be necessary.
Is there a need to introduce any of these glycated proteins, but have them in a state where they're non-reactive, but then they can be turned on either by the addition of, let's say, a second compound or, light or whatever other mechanism, so that they can get into a person and again, then be used at will instead of used immediately as soon as they're administered?
Yeah, you're actually thinking forward to one of our favorite applications of NSAAs. which is switchability. And right now, there are various ways to turn a protein on or off that have different degrees of spatiotemporal resolution. One of the things that has, a lot of people, including ourselves, excited about NSAAs is that we can make proteins that have NSAAs that are sensitive both to chemical compounds or, as you said, to light. Imagine a protein amino acid that has one conformation in one wavelength, and then it completely switches to a different conformation in a different wavelength. As protein engineers, we have experience building proteins with these switches that can allow them to turn the protein on and off. It could either, for example, disrupt the protein's fold, or it could even be as simple as covering up the active site of an enzyme or opening it back up again. So all of those are possible. And even on their own, those are powerful chemistries that are enabled by our platform. What you're getting to now is, I think, the incredibly exciting future of our field, which is combining multiple new amino acids at the same time. So when I talk about, recoding or reprogramming these organisms, right now, we're able to put one new amino acid into a protein at a time. We can put as many copies as we want, but we have to, we only have a freed up space in the genetic code for one of these new amino acids. Right now, we're finishing a new recoded organism, also a form of bacteria, which has 7 slots that have been opened up in the genetic code instead of just one. And so when that organism is complete, now you can start thinking about combining these different functions, right? So you could have a glycosylated protein that's switchable, and you can choose how to activate it, whether by a chemical or by light. But there's so many different ways you can imagine combining these different compounds. This has us very excited for the future.
Yeah, no, I was going to say kind of the same thing. I think with your background and with what you guys are doing there, many very positive applications. So I think, GRO Bio is going to do very well, I hope. Any last items that you want to point out that I haven't asked you about? If not, we'll give listeners a resource and where to go to find out more. But go ahead.
No, this has been fantastic. I mean, I think maybe one of the aspect of the company I'd mentioned is, as you talk about challenges that face the field, one of the hardest things about expanding the amino acid alphabet in an organism like ours, or really any organism, is that you have to engineer what we call translational machinery to install that new amino acid. These are the components of the cell, that act like the factory parts that put the new amino acid into a growing protein chain. And there are really 2 parts to them. There's an enzyme and a tRNA. And it's really been challenging for our field to create those translational machineries in an efficient way and a way that's very active and specific. When I talk about specificity, you can imagine how important it is that you don't have crosstalk between this machinery and the endogenous machinery in the organism. You don't want to stick non-standard amino acids where they're supposed to be standard amino acids, and vice versa. So, when I was a postdoc, and even the 20 years prior to that, engineering that machinery is a multi-year project. It might be someone's Ph.D. dissertation. That's the level of challenge we're talking about. So one of the things that we wanted to do at GRO Bio is dramatically accelerate that process and make these translational pairs much more specific and active to the target amino acid.
I just realized something. I hope this is what if you were to engineer some of the bacteria that make up your microbiome and give them these new abilities and modify them instead of the person? Bacteria are very good at making all kinds of compounds. You may be able to accomplish an endogenous factory by turning on, again, gut bacteria to produce X, Y, or Z when they don't normally do it. And it might be an easier time than modifying the person.
Absolutely. And there are companies working on engineering bacteria that secrete therapeutics, for example, or otherwise improve the physiology of the environment where they home to. And you could certainly imagine engineered versions of those that secrete proteins that have these non-standard amino acids, right? There's no reason to be more fearful of a therapeutic that has a non-standard amino acid or a standard one. That's one of the things I'd mention is that there already are blockbuster drugs on the market that utilize non-standard amino acids. They have to be installed through a very expensive chemical process, and it's you can't really oftentimes choose where or how to engineer them. But for example, Novo Nordisk has a GLP-1 agonist called Ozempic, which utilizes a non-standard amino acid to improve stability of that protein. So, these engineered systems, I think we should, treat them like any other therapeutic. They have to be tested. But, both the idea of using cell-based therapies, like as you described, and cell-based therapies that secrete proteins with non-standard amino acid could be very powerful for patients.
Okay.
Yeah.
Well, very good. What's the best way, again, for people to find out more? Should they go to growbio.com or how can people follow up and keep track?
Yeah, growbio.com is a great place to go, grobio.com. We're on Facebook, Instagram, Twitter, and you can find links to all those channels through the website. And of course, you can also reach out via contact form on that page if you're interested in opportunities with the company. We're always looking for great talent. We're always looking for new collaboration opportunities. And we're also just looking to have fun conversations with like-minded individuals. So if any of this is of interest, please feel free to reach out to me.
Great. Well, Dr. Mandell, thanks so much for coming on the podcast. It's been a good call. Thank you.
Yeah, thanks, Richard. It's been a pleasure. Thanks for the time.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.